And so we're thinking, okay, how do you have the highest energy density possible?
Yeah.
And it's like, well, you go to Wikipedia and there's, there's antimatter. Okay, that's a little impractical. We don't know how to get antimatter. And then it's nuclear. Okay, it's a little difficult to get our hands on. Maybe we can do something there. And then there's chemical, and it's like 70 times higher than the lithium-ion battery.
Yeah.
And you're like, great. If I'm 10% efficient, it's 7 times as energy dense.
I've never met anyone like it.
He could hack anybody's phone in a matter of minutes. Who is that guy? Who can do that?
Thomas is the most interesting man in the world.
He's one of my favorite people on the planet. Inventor.
Wicked smart.
The master of cutting corners.
If you had a dead body in your trunk, who would you call?
He would get arrested immediately in a lineup.
I stood in line to get his autograph.
His mouth can barely keep up to his brain.
I don't actually know what Pablos does.
A hacker magician.
Man of the future. Future.
So that wasn't gonna.
Yeah.
Okay, so 40 years in the wilderness, then you start Lightcell. So it's how that happened.
So I was thinking, one of the challenges with Lightcell was that we were nice to have. We were trying to solve a civilizational problem, which is how do you do energy storage for grid electricity so that it can be green, which is nice.
Yeah.
But it's not the most valuable power that you desperately need.
Right.
I'm thinking, the problem isn't that we can't make something shiny. It's that we need them to be desperate so that it's still, no matter what, like they're still pushing for it. Like even before we have, so initially we thought, okay, instead of doing grid arbitrage, energy storage, let's find something that has much higher energy density so people could not otherwise do it. And therefore, this is sort of a Peter Thiel thing, have a monopoly around that.
Yeah.
That's a great franchise. And so we're thinking, okay, how do you have the highest energy density possible?
Yeah.
And it's like, well, you go to Wikipedia and there's, there's antimatter. Okay, that's a little impractical. We don't know how to get antimatter. And then it's nuclear. Okay, it's a little difficult to get our hands on. Maybe we can do something there. And then there's chemical, and it's like 70 times higher than the lithium-ion battery.
Yeah.
And you're like, great. If I'm 10% efficient, it's 7 times as energy dense.
Yeah.
I'm thinking to myself, the difference between a nickel metal cadmium battery and a lithium-ion battery was like what, 3x, something like that in energy density, 100 times as much usage. Something like that.
Right.
Like what do you get for 7 times? What do you get for 20 times? Mm-hmm. Okay, how do you do that?
Yeah, the premium on being, 1x better is that you win the whole market.
That's right.
And so if you could get 7x better, you should win the whole market.
The whole market.
Yep, okay.
Transform everything. So I'm like, okay, well, that's a very attractive way of thinking.
Yes.
What are the fundamental ways to get energy out of this? And I'm thinking, well, we have heat engines, all these different scalings.
Well, let's talk about
rocket. Yeah.
So first way is Carnot.
Yeah.
Which is what ICE engines are all doing.
Well, not quite.
Well,
but
I
sure,
guess
they're bounded by it. They do.
They're bounded by it. But basically, we burn the shit. We make heat. We heat up water. We make steam. We compress a turbine. Or get a turbine going, and then get a generator going and spit out electrons. So that's basically what we're doing in a normal generator.
Yeah.
And then people are fantasizing about Stirling engines and these other thermionic converters to get heat and more directly into electrons. And what's the max there? 30% efficiency or something?
So it's something like
okay.
that.
But 30%.
A little more. Yeah.
30% efficient.
Yeah, would still be.
Is what we're getting. So what's an ICE engine? 20?
So
17?
It ranges a huge amount depending on what it's optimized for.
All right, but it's still better than batteries by a lot.
Yeah, like 20 to 60.
Yeah,
like,
but they're already living off of the logic that you...
no, that is,
All gas engines are living off of the logic that you just described.
To some extent.
That they're way better than batteries.
Right.
So that's
why they're living off the energy density.
Yep, that's right.
Which means that despite the fact that if you have a battery, it has very many fewer components, much less going on compared to an engine that has 2,000 different parts.
Right.
It's been heavily cost optimized because it's been so central. And even at small scale, you're not even going to get, in real world use, you're not even going to get 20%. Whereas in the peak usage of like a giant man diesel engine that's so big that like it's very difficult for it to radiate energy out, they're getting like 60%.
Okay.
Yeah. To drive like a
percent of the 70x.
Yeah, like as work. Like then there's magnetic.
So I'm getting 40x a lithium ion battery, basically.
Yeah.
Measured by weight or volume or something.
Yeah, but then you have to account for all the other, the engine.
Yeah.
Which it turns out to be quite a lot. And then if you look at it, it's not really.
But it wouldn't. For a generator, it's sitting on the ground anyway. That's different than putting it in the sky.
Yeah, that's true.
To really matter.
That's true. That is true. But the more material that you use, which depending on how you count it, if it's dollars per kilogram, it's the thing, and everything kind of scales with that. The more expense and balance of system. But it at least drives down towards the cost of materials. So it's not too.
Okay.
Yeah.
But anyway, all right. So there is a history of converting fuels to energy.
Yeah.
Why do you want to do it again?
So I was looking at the fundamental scaling laws of doing it via a heat engine or doing it photonically.
Okay.
So, and the first thing that I looked at was something that I knew a lot about, which is, and everybody does, first year physics, like the Stefan Boltzmann law, it's T to the fourth is how much light is coming out. And as you get hotter, it changes color, And I was like, well, you can have spectral selectivity and have the light come out and excite a solar panel and reflect everything else.
Yeah.
What's the limit to that? And it's like, well, it's like to a very ideal approximation, it's not clear that there is any limit.
Wow.
But then when you put in the practicality, the practicalities matter a lot because you have a lot of recycling. So if it's bouncing back and forth many times, and you're losing only 1%, that ends up adding as many times as you bounce. Sort of compounding, right? So then it's like, so it is a practical matter primarily. But then I started looking at, and thinking about the thermodynamics, and it seemed to be that it could be something like a fuel cell, where you're not actually limited by Carnot efficiency at all. Although again, it's not ever clear if in a practical system that you would surpass Carnot, but theoretically that you could, and this is extremely interesting. So I started thinking about alternative ways to make light. And I was like at a steel mill at one point. I saw a green flame. I was like, what's with that? Like, oh, there's probably some copper.
Yeah.
And I'm like, I start studying this before the 4th of July and start studying what's the cause of different colors of flames.
Yeah.
And there were all sorts of things that I thought I knew that it was just not the case. Like people were at the time making fun of some entrepreneur. They're like, oh, I don't know if she's blue flame enough. And I'm like, you probably don't even know why a flame is blue, because it's not temperature. It's the specific chemical reactions. And when I looked at every different atom in the world, what the brightest light was and the most monochromatic was sodium.
Wow.
And I was like, that's fascinating.
Yeah.
So, and I started studying, okay, well, what is the real peak brightness of this? What would the limitations be in terms of power? And the first calculation I did was like, holy crap, this has, in terms of the amount of circulating light, not the amount that finally gets out, but it's like you could have megawatts in a liter. And I'm like, well, that's a lot more than I was expecting.
Wow.
And then I the 4th of July fireworks show. I'm swinging around to take people's pictures of their faces, and their faces are lit up. And I'm like, okay, what's the real limitation here? I found some unclassified documents on the bizarre efficiency of sodium nitrate flares. It's been unclassified. These were these parachute flares that were dropped in like Vietnam, and they would light up a whole square kilometer.
Wow.
And sodium nitrate magnesium flares. And they're like basically trying to explain to themselves why it is that they get so many more quanta of light out than there are sodiums in the thing. It doesn't make sense with traditional thermoluminescence.
Okay.
So now I'm like, okay, that's really fascinating because that suggests that this is thermally driven or supported somehow. So if I can drive in energy from this end, can I get energy out this end in this specific wavelength? And so then I go and I look and I'm like, isn't there any kind of solar panel that matches this? So the way solar panels work is, depending on the material's band gap, when the photon is absorbed and excites an electron in a hole pair, the energy that of those being created is equal to, is held at a specific number. It's sort of like a minimum speed on a highway.
So does band gap in a solar panel need to be tuned for the frequency of the light?
That's ideal. That's ideal. Like the dream is that they're almost exactly on top of each other.
Right. Okay. Got it.
You just have enough to get absorbed by whatever it is.
Yeah.
And so I found that that people had just been mastering this.
Okay.
As the top layer of space solar cells to match basically it splits up, so they're absorbing sort of, orange and yellow and up, and then red and up, and then like infrared and up, and that's it. And I was like, hey, can we use that?
Yeah.
We can go on, but there's some interesting ideas that we found later for how to maybe decide between using these specialty cells versus silicon, which is still an interesting question. But from that point, I was like, wow, the efficiency, when I started calculating it, I'm like, wow, it could potentially, theoretically, I'm not sure if we'll ever practically do this, but potentially break 60%. And as a topping system that you could merge with something that boils water or spins a turbine, and then you could have world record efficiency.
Sure.
Yeah.
Right.
So and something
get heat too. So why not?
And the other thing is that the power scaling was extremely high with temperature.
Yeah.
So you could make a very, very, very small and lightweight thing, and super efficient, and it could burn because it's thermally driven. You could burn any fuel. So then I'm like, all right, this is fabulous. Incredibly consequential.
Okay, so let me just rewind and see if we can explain. So basically, you take any fuel that burns to get heat. You heat up the sodium to whatever temperature, and you get this light out that's incredibly monochromatic. It's a narrow band. It's very fucking bright.
Yeah.
And then the photons coming out of that, you send to a solar panel. You collect in a solar panel that is basically tuned for that.
Yeah, and much higher intensities. So maybe,
high intensity. And we have solar panels for high intensity because we made them for concentrated solar.
That's right.
Okay, so all that part exists. Might not be a huge market or something for that.
Yeah, you might have to scrounge and find people out of retirement who did concentrated solar, et cetera. But
but who's good at that? I wonder. Okay. So so in practice, what you want to build is essentially a thing with no moving parts other than maybe a valve and a spark plug or something.
Yeah, like a fan basically to cool the solar cells.
Yeah.
And secondarily, you might be able to get away with one to actually move the air through the system.
Okay, so is it fair to call this thing like a desktop Dyson sphere?
Yeah, you could say, although we're talking about, so jumping forward a bit, like the big scales that we're talking about building are, for data centers, is like 10 megawatt power plants in multiples. And then also at smaller scale, so basically, whatever it turns out you're going to need to run Kimi K3 and derivatives.
Yeah. Okay.
For businesses, we will make that too.
Right. We'll make it that size.
Yeah. Exactly. Out of N, like, those quartz backyard heaters that have a big column of flame. Well, if you ever put salt in that, you'll notice it's glowing quite yellow. If you increase the temperature, the brightness goes up considerably. We wrap those in silicon.
Try that again. So, what quartz backyard thing are we talking about?
Oh, so like if you're at a restaurant or something and there's like a heater,
right.
and there's like a pyramid heater,
right,
and there's like a big quartz tube.
Oh, that's a quartz tube.
Yeah, those are a quartz, and they're mass produced.
Pain in there.
Yes.
Right. Okay.
And it turns out if you just have salt in there, like even though it's not that hot a flame, you'll already start to see the yellow.
Oh.
But if you do what we're doing, which is to recycle the energy of the exhaust after it's been glowing, so it's still like more than 1,000 degrees, and it provides that energy into the air before combustion, then the temperature is driven to a very high level.
Okay.
And the brightness goes up nonlinear. It goes up almost exponentially.
Wow.
And so that means that basically, what we heard from the founder of SunPower, this is jumping ahead of it, but is that basically the cells that they make for one sun can tolerate up to 7 suns. And so you wrap it, we've achieved 7 suns almost.
Yeah.
And you wrap it with these silicon solar cells, and well, then it turns out, again, this is jumping forward a bit, but both when you overdrive the sodium and when you add potassium, it makes a very good spectrum for silicon.
Oh, okay.
So it turns out we don't need the extra expensive ones.
That sounds like a patent you should have filed, but okay.
I think I filed some patent.
Okay, so people can visualize. What we're really talking about is very simple. Kind of like that restaurant heater you described. You're basically doing the same thing. Just putting in gas, burning it, heating up, and then you want to like recycle the sodium.
We want to recycle it so that the exhaust
so it's
is running alongside or in the reverse direction, the incoming air, so that the incoming air before it hits the fuel is already ripping hot.
Yep.
So that the extra energy makes it extraordinarily hot, and that means that it gets super bright.
All right, so this is a classic over engineering, but I'll trust you on that. So, but where it goes is, the fuel itself is sort of immaterial as long as it gets hot enough. So you could burn, and like hydrogen burns super fucking hot. Yeah. So this whole thing could be zero emissions if you have a fuel like hydrogen that burns clean.
That's right, and
you could do it anywhere.
That's
anywhere you can have a fuel.
That's right. And somewhat coincidentally, like one of the hydrogen's amazing, but one of the dangers is the flames are very difficult to see in the sun.
Yeah.
If you have the salt around, it's very visible.
Right. Oh, that's interesting.
Actually, it's much safer.
Yeah. Good use.
It turns out we rely on this. But yeah.
I mean, I think you want to basically just burn hydrogen.
Makes water. Yeah.
As soon as you get it anyway.
Yeah.
And
it's pretty much. Yeah.
But for now, you got all these data centers that are basically burning natural gas. We have a huge...
Yeah, so we do experiments with hydrogen and propane and natural gas. And previously, we had mostly done propane. We did a little bit of methanol. We did a little bit of, kerosene, things like that. And then we have been recently trying hydrogen, and hydrogen works great.
Of course, yeah.
It burns super hot,
right?
And it is extremely spectrally pure because there's no soot at all. So it's somewhat easier to do experiments where you know exactly what's going on because you don't have carbon.
But this thing, if you're burning hydrogen, it could be hot enough you could crack methane with it and spit out carbon black and sell that. I don't know if that's useful.
So actually, let me show you since you mentioned. Yeah, I'll bring it to the camera, I guess.
Sure. Here, I'll see how that looks. All right, back up. I'll tell you what to do.
Yeah.
Yeah, okay, that's like...
See how fuzzy that is?
What's that made of?
So we were operating this is made out of alumina. It's a very high temperature heat exchanger. and we were operating this with an exterior annulus, which was feeding a torch, which is on this side, also made out of alumina. And on the inside, and from this side, we were injecting fuel.
Okay.
And during this test, we were injecting too much fuel. So relative to the amount of air that was flowing. And so when we stopped the test, we're like, hey, that's funny. There's flash graphene that we've produced all over the face of the thing. It's like this Vanta black velvet.
Right.
Wow, that's interesting. So you can do these interesting chemical reactions,
right?
And for production, because you have high temperature heat exchangers that allow you to very efficiently recycle the energy.
Yeah.
And then you put in the reactants, and they go towards their thermodynamic minima.
Yeah.
At whatever those controls are.
Distraction for you right now, but in the future it could be all kinds of.
Absolutely. I'm excited about this. Flash graphene. I can't believe we just accidentally made it.
Yeah. Right.
Yeah.
That's cool.
Well, I'm clear as to the what the quality is and if we could sell it, but there is a very high price for such.
There has been.
I think it should
people have figured out
large amounts,
ways to make graphene. We have a team that figured out how to make carbon nanotubes at scale they're ultra long.
Oh yeah.
Finally, so going back to your compressed air tanks, it's like carbon.
Yeah. No, they're much strong. It's much stronger.
Better.
Yeah.
So cool shit like that's coming. But yeah, you don't need to worry about it right now. But that's cool.